Hi everyone, my name is Tejas Chopra, and it's an honor to be presenting at the Storage Developers Conference 2023. My topic is energy efficient storage architectures. I'm a senior software engineer at Netflix, and through this session, I would love to share my learnings and views on how you can build storage architectures that are better for the environment. The agenda for the talk is as follows. I'll go over a brief introduction about myself, what I do. We'll talk about the benefits of energy efficient storage. We will then talk about some specific technologies in storage that are more energy efficient, a design of the storage architectures that is better for the environment. Finally, we will talk about how different cloud providers are employing energy efficiency techniques in their different services and applications. I would like to end by exposing you to some of the tools that you can explore to check how efficient your code or your architecture in terms of storage is. I'm a senior software engineer at Netflix. I work on architecting storage and transfer infrastructure solutions for Netflix studios. Netflix does not just stream movies, it also creates movies. And movie making is a more nuanced process. In movie making, you have petabytes to exabytes of data that is continuously ingested into your ecosystem, out of which only a small sliver of it actually makes it into the final cut. Moreover, every piece of data that you've collected has to go through many cycles and transformations. If you think about the movies that you're watching also, there are many devices on which you watch the movie. Each device has a movie that is rendered for that device. So you can imagine that just a particular shot can be transformed in multiple ways to add color or rendering. And therefore, the storage and the transfer side of the movie making process involves a lot of data, which is why it is important to make it efficient, not just in terms of performance, but also in terms of its energy. I'm also a founder at GoEV1, which is a thought leadership platform for immigrants. I'm a TEDx speaker, and I have spoken at multiple conferences on cloud computing, blockchain, software development, energy efficient computing, and engineering leadership. My career has been in companies like Box, Apple, Samsung, Cadence, and Datrium, where I was focused mostly on backend infrastructure and storage. Let us dive into why we even need to study or even learn about energy efficient storage. There are multiple reasons why energy efficiency is important when it comes to storage. Let us first tackle the economic savings. Energy efficient storage actually reduces the power consumption. It leads to savings in electricity bill. A 10% reduction in energy usage can lead to a 1% decrease in the total operational cost for many data centers. This is just on the operational side. If you think about the infrastructure costs, then the reduced heat generation means that you need less cooling, potentially saving costs on cooling equipment and maintenance. Let us now talk about the environmental impact, specifically the carbon footprint. Energy efficient storage architectures can significantly reduce the carbon footprint of data centers. For instance, a data center that uses 1 megawatt of power annually might emit over 5,000 tons of carbon dioxide into the environment. Efficient storage can reduce this by hundreds of tons. Also, let's talk about the next important part in environmental impact, which is the reduced resource utilization. Efficient storage often requires fewer raw materials for manufacturing and less water for cooling, leading to more sustainable operations. As the world's data needs grow, the demand for storage is increasing. Efficient storage architectures allow data centers to meet these needs without a linear increase in energy consumption. There are faster access times, reduced wear and tear of equipments, leading to increased equipment lifespan. For instance, SSDs, being energy efficient, also end up providing faster read-write speeds than HDDs. Less heat, as we've explained before, reduces the risk of equipment failures, ensuring smoother operations and less downtime. According to the Natural Resources Defense Council, the data resources in the US consumed approximately 215 terawatt hours of electricity in the year 2020. And that has increased to around 300 terawatt hours of electricity in 2023. That is enough to power over 20 million homes for a year. Global data center electricity consumption is projected to increase to 651 terawatt hours by 2025. Without energy efficient storage, this figure could be 20% higher. The International Energy Agency reports that data centers and data transmission networks combined account for about 1% of the global electricity usage. Implementing efficient storage architectures can reduce this percentage number significantly. It means that there are lesser fossil fuels that are burnt to generate electricity, resulting in reduced greenhouse gas emissions. As you can see, there are significant benefits to building architectures that are efficient for the environment and energy. Let's now dive into some of the energy efficient storage techniques that you can employ and learn about. As you can see here, some of these terms you may be familiar with. For example, SSDs. A lot of us know that SSDs do not have any moving parts, unlike traditional hard drives that have spinning disks and moving read-write heads. SSDs store the data on NAND flash memory, and so they consume much less power, especially during idle times. While a hard drive may actually use 6 to 7 watts, an SSD may just use 2 to 3 watts. Due to their lack of moving parts, they can access data much faster, further reducing the time that they need to be active and consuming power. And according to Storage Review, SSDs use approximately 50% less power than hard drives. Over a year, this difference could result in substantial energy savings, especially in large data centers. The other important concept in storage is phase change memory. Phase change memory, or PCM, stores data by changing the state of the material from amorphous to crystalline. It combines the speed of DRAM with the non-volatility of flash memory. So it is actually non-volatile, which means it is persistent. It offers faster data transfer rates than traditional memories and can endure at least 10 million write cycles that make it more durable. So as you can see in this diagram here, phase change memory fits somewhere tightly between the NAND and the DRAM that is present. DRAM, of course, and SRAM are memory techniques, whereas NAND and HDDs and SSDs are storage. And phase change memory is a storage class memory that fits right between them, which offers us the speed that is closer to the memory and offers us persistence, which is closer to what storage provides. The next one is MRAM, which is magnetoresistive random access memory. It uses magnetic states instead of electronic charges to store information. You can imagine, because it is not using electric charges, they consume less power. They do not need a constant flow of electricity to retain the stored data. They are also faster and have a longer lifespan than traditional NAND flash. The last one that we would like to cover is the SRAM, which is the spin transfer torque magnetic random access memory. It's the STT MRAM, actually. This is a type of MRAM where data is written by aligning the magnetic orientation of tiny metal layers within a memory cell. STT MRAM combines the advantages of both DRAM and SSDs. They are non-volatile again, consume much less power, and provide rapid data transfer speeds. This unique design ensures reduced power usage during write operations. While energy-efficient storage technologies like SSDs and MRAM may have a higher upfront cost than traditional hard drives, their long-term savings in power consumption and increased lifespan often justify the initial investment. As data demand grows, the need for fast, reliable, and energy-efficient storage becomes paramount. These technologies are just trying to cover at a very high level what could be used to meet the storage needs of the future while staying under the boundaries of energy efficiency. Now that we've talked about some some technologies that are used in storage, let us step back and look at how you can design architectures that are more energy efficient. In fact, a study in the University of California, Berkeley, said that a meticulously planned storage architecture can lead to significant energy savings with potential reductions in energy up to 70%. In a study by SanDisk, databases that were using flash-based caching improved the performance by up to 5 times and used 80% less energy. Uh, I also read a report from Dell EMC that suggests that intelligent tiering of data, which is identifying which other tiers or which data is hot and cold, can lead to up to 90% savings in storage costs and greatly reduce the energy usage. Data compression is another technique that could reduce the energy usage by up to 70%. In this diagram, we are trying to cover most of these techniques. Let me just walk you over this. We would love to build a storage architecture that can reduce the footprint of data on cloud. A very good rule of thumb is the lesser your footprint on cloud and the cheaper that your storage is, the more energy efficient it inherently becomes when it comes to just the bits that are stored. Here we are leveraging several techniques in this diagram, like deduplication, compression, along with encryption. And there are some that we are not showing here, such as thin provisioning and erasure coding, which again help us reduce the footprint of data. The idea is very simple. When you have data that you want to upload to cloud, you can have an intermediate on-premise system that absorbs most of the reads that are sent to that requesting that data. When you want to write the data, the first step is you want to check if there is the data already present on cloud. This step is called deduplication. In this step, before your data is uploaded to cloud, you check in a global fingerprint table or a global hash table, which contains hashes of all the content that is present on cloud buckets. If your data is already present in cloud, you would see a hit in this global hash table, and you do not need to upload the data to cloud. However, if it's the first time you're writing this data, you would compute the hash of the data, put an entry in the hash table, compress the data after deduplicating it, write the data locally to a local storage. Finally, you encrypt your data and then upload it to cloud. Once the data has made it to cloud, you would update your fingerprint table or the hash table with the location of that data in cloud. The next time a similar data is written, you would see a hit in your hash table and you do not need to upload your data to cloud again. What this effectively does is it has leveraged the technique of deduplication, which is not having duplicate entries in cloud even before the data is sent to cloud. Secondly, it also tries to compress the data locally and then upload the compressed encrypted bits to cloud. Thirdly, it applies compression only after it applies encryption only after it has deduplicated and compressed the data, which means that encryption is the last stage just before the data is put to cloud. By doing that, you actually give yourself a chance to compress the data because it is nearly impossible to compress data that is already encrypted. This is a very simple way of reducing your cloud footprint and making your storage architectures very energy efficient. I briefly touched upon how thin provisioning and erasure coding can also help reduce your architectures, reduce your energy, the energy that is released by your storage infrastructure and architecture. As you can see here, designing an upload and a download of data to cloud in an efficient way can significantly impact the footprint of data on cloud, reduce your costs, and also make it more energy efficient. Let us now look into what different cloud providers have done in the field of energy efficiency. We've just covered the major cloud providers, AWS, Azure, and GCP, and I'll briefly touch upon these cloud providers. For AWS, let's first talk about the electric system overhaul. Think of an electric system as the heart that pumps blood or electricity to the body, which is the data center. A more efficient heart means less energy is wasted and more is used when it's needed. Traditional power conversion processes can waste between 5 to 10% of the electricity they handle. AWS came up with a new system where they could potentially save hundreds of megawatt hours annually, translating to reduced greenhouse gas emissions. They use, instead of manually adjusting the air conditioner or the cooling side, AWS leverages machine learning like a smart thermostat to predict the best temperature settings. This way, the system avoids cooling the room more than necessary. Cooling can account for up to 40% of the data center's total energy consumption. By optimizing the cooling, AWS can reduce this figure significantly. Assuming that even there is a 10% improvement because of these machine learning optimizations, this would result in significant annual energy and cost savings. Instead of relying solely on traditional energy sources like coal or gas, AWS aims to power its entire infrastructure using clean energy sources like wind and solar. AWS, up until 2021, had 127 renewable energy projects that generated over 6.6 gigawatt of renewable capacity. Achieving a 100% renewable energy goal would place AWS amongst a select group of businesses reducing their carbon footprint substantially. Let us move on to Azure. Microsoft is also using AI to make both their equipment and programs smarter. With AI, systems can predict and adapt to needs using just the right amount of energy. AI can actually help reduce the data center usage by up to 15% as it is optimizing the workloads and reduces the wasteful processes. Microsoft also came up with a project Natic, which is focusing on subsea data centers. In short, imagine a data center placed underwater in a sealed capsule. The cool underwater environment naturally helps in cooling the system, saving a lot of energy usually used for air conditioning on land. Traditional data centers can use, like I said, up to 40% of their energy on cooling. And with this project, Microsoft reported that the underwater data center had a failure rate of just 1/8 of what was seen on land, demonstrating reliability and potential energy savings. By 2021, Microsoft had reduced its carbon emissions by approximately 730,000 metric tons, which is an equivalent of nearly taking away 158,000 cars off the road for the year. They have pledged not just to reduce, but to remove their footprint from the environment by 2030. And Microsoft is not just relying on reducing emissions, they are actually actively investing in projects that generate clean energy like solar or wind farms. By 2021-22, Microsoft had procured over 20 gigawatts of renewable energy, which can power around 2 million homes. And they invested $1 billion in climate innovation funds that focus on carbon removal. Let us now finally talk about GCP, which is Google's data center and Google's cloud storage infrastructure. Traditional data centers can waste 30 to 40% of the electricity that they pull off the grid. Google came up with data centers that use 50% less energy. And their advancements ensure only up to 10 to 15% wastage when it comes to pulling the energy off the grid. This is a significant improvement in efficiency. Google, again, like Microsoft and AWS and Amazon, uses artificial intelligence to predict when its data centers will get hot and to control the cooling systems. And it has achieved 40% reduction in cooling energy. Google designs its own data centers, and that makes it very different from the other providers. Its custom servers and voltage regulators improve energy efficiency, and their servers use a 12-volt design that improves the power distribution by 2%. Like Microsoft, Google also pledges to be carbon neutral. And by 2017, actually, since 2017, Google has matched 100% of its global electricity consumption with purchases of renewable energy. This is how different cloud providers are actually working on improving the footprint of cloud in terms of the carbon footprint of cloud. And as machine learning and AI are aggressively increasing the footprint on cloud, there will always be a need to develop better systems, more intelligent ways in which we can reduce the impact. Most of you would be aware that even with machine learning and AI, Many companies right now have sprung up that try to optimize the models. What that does is not just saves cost, but also the environmental impact. If your machine learning model can use lesser GPUs or can be trained in faster amount of time, it releases lesser heat into the environment. And consequently, it is better for the environment. Finally, let's talk about some tools that you can use to measure your carbon footprint impact or your software's carbon footprint impact. These are tools that some of them are open source, some of them are actually given out by the cloud vendors. Cloud Carbon Footprint Calculator estimates the carbon emissions associated with different with cloud usage across AWS, Azure, and GCP. It analyzes the cloud spend data to estimate emissions. Code Carbon is an open source CLI tool that calculates the carbon emissions of specific lines of code or cloud services used. It integrates with popular IDEs like Visual Studio. Carbon Diet is a SaaS tool that analyzes code bases to identify optimization opportunities to reduce redundant computing. It generates actionable insights and estimates potential carbon savings. The AWS Carbon Footprint tool estimates the carbon footprint of AWS services, and it takes into account usage types, power sources, efficiency improvements as well. Similarly, you have the carbon impact dashboard from Microsoft, which estimates the emissions from Azure services that are used, and the Google Carbon Footprint, which measures the carbon footprint associated with the GCP platform. The Green Software Foundation Carbon Rating is an open source standard that rates software based on a scale from A to F for carbon efficiency. It performs a static analysis of code to estimate emissions. There are a variety of open source and commercial tools available for software teams to analyze their carbon footprint. By leveraging these, many architects can identify the optimization opportunities and compare their design decisions based on the sustainability impact. Hopefully, this presentation was able to throw some light on energy efficient storage architectures and how you can, in the future, when you're designing efficient architectures, use some of the tools. That's my time. Thank you so much for listening in. Please feel free to follow me on LinkedIn by scanning this QR code. And please take a brief moment to rate this session. Thank you so much.